Welcome to Space Dreams documentary. Tonight the universe turns quiet and precise. Starlight softens. Shadows glide across distant suns. Tiny wobbles whisper of unseen worlds. Gravity briefly focuses a faraway glow, and a faint point of light holds its place beside a star. This is how exoplanets are found, not by sight but by patience and pattern. If this journey helps the mind slow down, please like the video and subscribe to Space Dreams documentary. Turn on notifications for more calm cosmic stories. Now let the stars begin. A distant star appears steady, yet its light can carry a quiet interruption. Exoplanets become knowable when repeating patterns appear in starlight without any planet being seen. In a wide field of darkness, one point of light holds a smooth glow that seems almost unchanging. Over time, that glow can dip by about 1/10,000th like daylight, softened by a single thin veil of high haze. The dip returns with the same spacing, and the spacing matters more than the depth at first. Regularity turns a faint change into a reliable sign. The first unlock sits in the idea of repetition. A single dimming could be chance. A series of dimmings evenly spaced behaves like an orbit leaving a trace. The scene stays calm. A bright disk too small to resolve acts like a lantern behind frosted glass. A tiny silhouette crosses, and the overall brightness falls in a smooth curve. The curve rises back to its previous level and rests there again. This is the simplest promise of the search. Many worlds can be inferred from the way light is slightly missing. In that missing light, size, distance, and timing begin to separate from each other. The light does not need to speak loudly. It only needs to be consistent. The physical detail that matters first is the edge of the shadow. A planet has a crisp limb. It blocks a portion of the stellar face with a boundary that stays sharp. The star itself has a gentle gradient. Its center appears brighter than its edges because the line of sight passes through different layers. That soft gradient shapes the dip. The second unlock arrives here. A shadow across a graded surface makes a dip with a particular curvature. The beginning and end of the dip often slope rather than snap. The planet's path cuts a chord across the face, and the length of that chord sets the duration. The image remains slow. A bright circle shows a mild darkening toward its rim like a glowing ember with a softer edge than its core. A small dark disk glides over it, and the overall glow changes with a smooth patience. The drop is not a simple step. It is a rounded valley. The valley has shoulders. Those shoulders hold information about the path taken. A world that crosses near the center tends to create a longer, deeper valley than one that grazes the edge. This is geometry written into brightness. It is also a gentle scale shift. A planet can be smaller than a star by more than 100 times in radius, yet the shadow still leaves a readable imprint. The time scale can be hours for the crossing. The orbit that causes it can be days or years. The same shadow can be brief, yet its return can be spaced by seasons. When the spacing is known, distance becomes approachable. An orbit with a short period implies closeness to the star. A long period implies a wider loop. The third unlock follows from that spacing. Period and distance relate through gravity in a steady way. A longer year means a larger orbit. Even without naming the full law, the link remains dependable across many systems. The mind can hold it as a simple balance. Faster loops cling closer, slower loops wander farther out. The light curve becomes a clock drawn by motion. Yet brightness is only one channel. Light also carries a subtle texture in how its colours spread. In that region, a star's light can be thought of as a smooth band with fine dim notches. Those notches mark where atoms absorb certain colours. When the star moves slightly toward or away, the notches slide a little. Doppler shift is a change in wavelength caused by motion along the line. Two sentences can keep it grounded. A wave train squeezed by approach has shorter spacing. A wave train stretched by retreat has longer spacing. The importance is quiet. A planet does not only cast a shadow. It can also pull its star into a small back and forth motion. The star and planet orbit a shared center. The star's path is tiny, yet the wavelength shift can reveal it. This is another gentle payoff. A world can be inferred not from missing light, but from a slow breathing of the spectrum. The motion can be only a few meters per second for some systems. That is like a slow drift of a floating leaf across still water. The number stays small because the effect is subtle. The scale shift stays large because the masses involved are enormous. A massive star can still move slightly under the pull of a planet. In a calm mental picture, the star does not sit on a fixed pin. It traces a small loop. The loop is far too fine to see as a path. Its evidence appears as a recurring slide in the fine notches of light. The two methods, shadow and shift, feel different. One asks for alignment. One asks for motion along the line. Together they show how indirect discovery works. A signal would not need to be dramatic. It needs to be coherent across time. The visual anchor changes. A band of light stretches like a faint ribbon and thin dark grooves sit across it. Those grooves drift slightly left, then slightly right, returning like a tide that never reaches a storm. The payoff here is that mass begins to separate from size. A deep transit suggests a larger radius. A stronger wavelength swing suggests a larger mass. A world can be dense or puffy. The combination of clues can hint at that difference without ever showing a surface. Now the limit of intuition arrives softly. Small changes invite false causes. Stars have texture. Dark regions can rotate into view and out again. A bright flare can briefly raise the glow. Granular convection can cause a restless shimmer. These effects can mimic a dip or complicate a shift. The limit is not in the idea of patterns. The limit is in separating overlapping patterns that share similar timescales. If a star's rotation period resembles an orbit period, the signals can blend. If brightness noise varies on the same hours as a transit, a shallow dip can vanish. If the notches in light drift because of surface flows, the motion can look larger or smaller than it is. Resolution also draws a boundary. A dimming smaller than the natural flicker can hide. A motion smaller than the stability of the notches can be lost. The safest approach is patience. Long baselines help. Repeated cycles help. Still, some worlds remain beyond reach because the star's own variability becomes the dominant voice. The mind can accept this as a soft horizon rather than a failure. Some systems simply refuse clarity from these signals alone. Another payoff settles in after that horizon. Geometry can rescue ambiguity. A transit seen from the side requires a near edge on orbit. Many orbits miss that alignment. A wavelength shift can appear even when no transit occurs, but then size stays unknown. The two methods complement each other because their limitations differ. The shadow needs a line of sight that cuts through the orbit plane. The shift needs motion along the line, which appears for many tilts. The scene returns to slow imagery. A thin sheet of dust in a beam of light shows a faint band. Tilt the sheet and the band changes thickness. Some angles hide the band entirely. The same happens with orbits. An orbit is like a plane in space. Only certain tilts let a silhouette cross the star from this viewpoint. The section ends with a calm promise that the next step is not a new mystery. It is a clearer map of alignment. In the next movement, orbit planes and viewing angles set the stage for which signals can appear and which remain silent. A planet can circle a star in perfect steadiness and still remain undetectable from one direction. Alignment decides whether an orbit ever draws a shadow across starlight or keeps the path hidden. In a wide star field, a single system can be imagined as a bright point wrapped by an invisible flat sheet. That sheet is the orbital plane. Inclination is the tilt of that plane from the viewing line. A small tilt changes everything. The first unlock is simple. A transit is not guaranteed by the presence of a planet. It is granted by geometry. Light behaves as if the star is a glowing disk and the orbit is a thin ring. Only when the ring edge lines up does the planet cross the disk. The central image stays slow. A pale ring of dust traces a circle around a distant glow. The ring tips by a tiny amount and the crossing line shifts away from the centre. The difference between a crossing and a miss can be a tilt that feels almost nothing at all. A second unlock settles in as distance enters the picture. Farther orbits have narrower chances. A close orbit has a wider shadow lane across the star's face. A distant orbit has a shadow lane that often passes above or below. The chance for a transit in a close system can be about 1%, like one leaf among 100 in a dense canopy. The number is small and still meaningful. Over many stars, a small chance becomes a steady yield. The physical detail is the width of the transit corridor. It is set by the star's radius and the orbit's distance. When the orbit is tight, the corridor is wide. When the orbit is wide, the corridor becomes thin. The scene shifts closer. The bright disk shows a soft gradient. Its rim is dimmer than its centre. A dark path that cuts near the centre crosses brighter layers and produces a deeper dip. A path that skims the rim touches dimmer layers and produces a shallower dip. The third unlock lives in that skimming case. A grazing transit can look like a smaller planet. It can also look shorter than expected. The shadow only clips the edge like a thin crescent of darkness, sliding along a softly lit border. The beginning and end of the dip become less rounded. The curve can feel sharper because the path is short. Geometry shapes the light curve before any planet property is considered. At this distance, even the word edge becomes a real boundary. A planet's limb is crisp. The star's limb is graded. When those two meet, the dip takes its particular form. The analogy for orientation can stay natural. Two layers of fog drift in a valley at dawn. One layer slides above the other with a small tilt. From one hillside, the layers overlap and look thick. From another, the overlap disappears and the valley floor seems clear. In the same way, an orbit plane can overlap the stellar disk or miss it entirely. A fourth unlock follows when multiple planets appear in mind. Many systems hold several orbits. Those orbits often share nearly the same plane. A slight mutual tilt can separate them. One planet can transit while another never does. The system can be rich and still look sparse. The visual anchor slows again. Several faint rings sit around a star like stacked halos. One ring aligns and sends a dark bead across the bright disk. Another ring tilts by a breath, and the bead passes above, leaving no dip at all. The scale shift becomes gentle and wide. The tilt can be smaller than a degree and change an outcome. The orbit can span millions of kilometers and still behave like a thin sheet. Time can shift from minutes at the moment of crossing to years between crossings. A fifth unlock appears as the idea of viewpoint expands. Some methods do not require a crossing. A star can still carry evidence of motion along the line. Yet that evidence depends on tilt too. If an orbit is seen face on the star's back and fourth motion along the line can shrink toward invisibility. The planet can still be massive. The signal can still be weak. The limit is in projection. Motion can point sideways rather than toward and away. Projection hides part of the truth. The mind can hold a simple picture. A circular motion seen from the side becomes a line. Seen from the front, it becomes a circle with no depth change. The star's spectral shift depends on depth change. Without depth change, the shift fades. This does not mean the planet is absent. It means the chosen line of sight is not favourable for that channel. The scene becomes one of slow rotation. A thin ring turns in space. Its nearest edge brightens slightly as it comes forward. Its far edge fades slightly as it recedes. Yet the ring's plane can also rotate without changing its tilt. That rotation can repeat without ever producing a shadow. In that region, a signal would only be present in certain dimensions. The sixth unlock arrives in the idea of inference. Alignment is rarely observed directly. It is inferred from the signals that appear. When a transit is present, inclination is constrained tightly. When no transit is present, inclination is open. The limit of observation sits here, and it is specific. Absence cannot be read as emptiness. A missing transit can be caused by a small tilt. A weak motion signal can be caused by face on geometry. Without multiple independent clues, the true orientation remains uncertain. Even with a clear dip, a grazing path can confuse size. Even with a clear motion shift, mass can remain a lower bound if the tilt is unknown. The boundary is in degeneracy. Different combinations of tilt and mass can resemble each other. Different paths across a graded disk can resemble different planet sizes. The light curve and the motion curve are both indirect. They are shadows and echoes of an orbit. The scene rests on a final, slow image. A narrow beam of starlight passes a set of faint tilted rings. Only one ring places a small dark notch on the beam at regular intervals. The notch returns like a quiet heartbeat, and then disappears when the ring tips by a fraction. The rhythm remains, the visibility changes, the transition forward stays gentle. The next section follows one of these crossings in detail, and lets the shape of a single dip unfold into measurement. Sometimes the clearer sign is a small absence that keeps time. A transit appears when a planet's silhouette removes a tiny fraction of starlight at regular intervals. In a quiet region of space, a star's glow arrives as a steady stream. Most of that stream changes only slowly. Then a shallow dip forms. It settles into a smooth trough. It rises back to the previous level. After a stretch of calm, the same dip returns. The first unlock is the return itself. Repetition turns a single dip into an orbit. The spacing between dips becomes the planet's year around that star. Even when the dip is shallow, the clock can be clear. At this distance, the star remains a point. The planet remains unseen. Yet time provides a handle. A visual anchor holds the mind steady. A bright disk is imagined behind a thin, even veil of darkness. A small round shadow slides across a narrow band of that disk. The shadow keeps a crisp edge. The band it crosses has a gentle brightness gradient. The shadow leaves the scene without a trace. Only the overall glow changes. The second unlock comes from the depth of the dip. A deeper dip implies a larger silhouette. A shallower dip implies a smaller silhouette. The depth is not a mood. It is a fraction of area blocked. If the star is a luminous circle, the planet blocks a smaller circle. A world that causes a dip of about 1% is like a field of 100 daisies, where one bloom is briefly shaded. The number is plain and safe. It carries an immediate sense of scale. A small fraction can still be unmistakable when it repeats. In that region, light behaves as a sum. Many rays arrive from many parts of the star's face. A transit removes rays from one patch at a time. That patch moves as the planet moves. The brightness curve does not drop in a single step. It slopes down. It holds near a floor. It slopes up again. The physical detail inside that slope is the edge of the silhouette crossing the edge of the star. Two curved boundaries slide past each other. Their overlap grows, then shrinks. This is geometry in motion. The third unlock is that time inside the dip matters not only the depth. The duration hints at speed. A faster orbit tends to produce a shorter crossing. A slower orbit tends to produce a longer one. The duration also hints at distance from the star. Close orbits move quickly. Far orbits move slowly. The scale shift arrives gently. Minutes of dimming can suggest a path that spans millions of kilometers. A short event can point to a system that persists for billions of years. Another slow image enters. A faint luminous circle hangs in blackness. A dark dot approaches its limb. The dot touches the rim, and the brightness begins to fall. The dot moves inward and the fall continues. The dot reaches the center band and the brightness rests in a shallow valley. The dot continues and the valley holds. The dot nears the far rim and the brightness begins to rise. The dot leaves and the glow returns to smooth steadiness. Each phase has a meaning. The start and end mark contact points. The flat middle marks a time of full overlap. The fourth unlock is the path across the disk. A central path cuts through brighter regions. A grazing path skims dimmer regions near the edge. The same planet can produce different depths on different paths. The same depth can come from different combinations of size and path. This is not a flaw. It is a clue that geometry must be included. A useful term can appear once and remain simple. A light curve is brightness tracked across time. It is like watching the glow of a calm ember as a thin shadow passes. It is like noting how a clear pond surface darkens when a cloud edge crosses. It matters because the curve holds timing and shape in one trace. With that trace, a transit becomes more than a dip. It becomes a signature. The fifth unlock comes from how certainty builds. A single dip can be noise. 2 dips suggest a rhythm. 3 dips establish a period with confidence. As cycles stack, the predicted next dip becomes precise. The predicted time narrows. The window shrinks. In that narrowing, an orbit becomes stable. A world becomes plausible. Another visual anchor arrives as a slow checkpoint. A sequence of identical valleys appears along an invisible timeline. Each valley has the same width. Each valley has the same depth. The floor of each valley is calm. The spacing between valleys is even. The entire pattern looks like gentle dunes in moonlit sand. The dunes are not carved by wind. They are carved by motion and alignment. The 6th unlock is that transits can reveal companions without showing them. If the timing drifts, another mass is likely tugging on the orbit. If the depth changes slightly over long spans, the path across the star may be shifting. These effects remain quiet. They appear as small departures from perfect repetition. They also open a door to multi-planet systems. Still, the section keeps its focus. The primary promise remains the clock and the silhouette. Now a soft limit arrives, and it is specific. The arriving starlight is not perfectly smooth. Stars can flicker and brighten on their own. Surface patterns can rotate in and out. The brightness can ripple like heat haze above a sun-warmed rock. This sets a detection flaw. A dip smaller than the natural flicker can hide inside it. A dip that occurs rarely can be missed between long stretches of calm. Another limit sits in sampling. The light arriving over time can be incomplete. Portions can be absent or blurred together. If the dip begins and ends between these moments, the true depth and duration can be distorted. A shallow transit can look deeper. A short transit can look long. The boundary is not in the idea of a transit. The boundary is in resolving the precise curve. Without a clean curve size and path entangle, another quiet scene carries that boundary. The star's glow trembles slightly as if seen through thin moving layers. The planet's shadow still crosses. The crossing is real, yet the valley becomes rough around the edges. The floor is no longer perfectly flat. Small bumps appear that do not belong to the planet. They belong to the star. This is the limit of indirect inference. The signal is drawn on a living surface of light. Even in this limit, an unlock remains available. Regularity can overcome texture. A repeating valley can be extracted from a restless background. Over many cycles, the shared shape stands out. The timing grows firm. The period becomes a stable anchor. With that anchor, other methods can later add mass. The transit supplies radius. The combination can hint at density and composition. The section does not rush there. It rests in the calm mechanics of a shadow that keeps time. A final visual anchor returns to pure geometry. A thin dark disk crosses a softly graded luminous face. The overlap grows and shrinks like 2 circles sliding in slow alignment. The dip completes and the glow returns to a steady stream. The next movement stays close to the dip itself. It lingers on the fine shape of the valley and how that shape carries more than size. A transit dip looks simple from far away, yet its curve holds quiet geometry. The shape of the dip reveals both a planet's size and the path it takes across the star. In a dark region, the star's face can be pictured as a smooth circle with a soft edge. The center appears brighter than the rim. The rim appears dimmer because the light comes through cooler, higher layers. That gentle gradient becomes the first key. A shadow crossing a uniform lamp would make a flat bottom. A shadow crossing a graded disk makes a bottom with subtle curvature. The first unlock arrives in the edges of the dip. The downward slope is not only a start, it is a measurement of how quickly overlap grows. The upward slope is not only an end, it is a mirror of how overlap disappears. A slow, steady image forms. A luminous disk shows faint concentric bands of brightness. The bands are not lines, they are smooth layers that fade toward the boundary. A small dark circle approaches the rim. The first contact looks like a tiny bite taken from the light. The missing portion is a thin crescent. It thickens with calm regularity. This crescent phase matters because it sets a scale for the crossing speed. The second unlock sits in duration. A transit lasting about 3 hours is like a thin cloud band taking the same time to slide across a full moon. Duration ties motion to distance. A faster orbit tends to shorten the crossing. A slower orbit tends to stretch it. Even when the star stays unresolved, time becomes a ruler. The physical detail remains the moving boundary between two curved edges. The planet's limb is crisp. The star's limb is soft. Where they overlap, the missing light grows along a curved front. This front moves like a quiet tide line. The curve of the tide line changes when the path changes. Now the dip's middle becomes important. A flat floor suggests the planet is fully in front of the disk for a while. A rounded floor suggests the planet spends more time near dimmer outer regions. The third unlock is that path and size can trade places. A small planet crossing bright center can mimic a larger planet grazing the edge. The curve can look similar in depth for a short time. The difference hides in the shoulders. The shoulders are the gentle bends where the dip transitions into the floor. When the path is central, the shoulders are smoother and the floor is steadier. When the path is grazing, the dip can become more V-shaped. The bottom never truly flattens. The scene slows again. A ribbon of brightness hangs in space like a pale stream. As the shadow enters, the ribbon sinks into a valley. The valley has two slopes. The slopes are not symmetrical when the path is off-center. One side can be steeper if the planet crosses a sharper brightness gradient. This brings a useful term once and keeps it light. Limb darkening is the star's rim appearing dimmer than its center. It is like a sphere wrapped in thin, glowing shells. It is like mist that looks brighter when seen straight through. It is like mist that looks dimmer near the edge where the view skims the surface. It matters because the dip shape depends on which shells are being blocked. The fourth unlock follows from that dependence. A transit can measure the star's brightness profile as well as the planet's silhouette. The same light curve contains two stories. One story is the planet's area compared to the star. Another story is how the star's glow changes with radius. The two stories can be separated when the curve is clean and the timing is precise. The ingress and egress set the speed. The depth sets the blocked area. The curvature sets where the chord lies across the disk. A gentle scale shift arrives. A boundary that moves by a fraction of the star's radius can translate into a path that spans millions of kilometers. The same curve can persist across dozens of orbits. Those orbits can continue for billions of years. Yet the information comes from a few hours of missing light. The fifth unlock is that the star's size itself becomes part of the measurement. If the star is larger, the same planet blocks a smaller fraction. If the star is smaller, the same planet blocks a larger fraction. The dip depth alone cannot give an absolute radius, it gives a ratio. The ratio is still powerful because ratios do not need distance to be meaningful. A world's size relative to its star can be found from the dip's depth. In that region, light behaves as a sum of many bright patches. Blocking a certain fraction reduces the total by that same fraction. Another slow visual anchor arrives. The star's disk appears like a soft peach of light with a gentle darkening near its boundary. A small dark bead slides across not in a straight center line but along a chord that sits higher. The bead's shadow covers brighter layers first. It then crosses into slightly dimmer layers. The dip responds with a floor that tilts almost imperceptibly. The tilt is the clue. The curve is not only deep or shallow, it can also be subtly lopsided. Now the limit of observation appears and stays specific. The dip shape can be distorted when the star's surface is not uniform. Dark regions can rotate into view and change the baseline brightness. Bright regions can do the same. This can bend the shoulders of the dip. It can change the apparent depth. Another limit sits in time sampling. If brightness is measured too sparsely, the sharpest parts of ingress and egress can blur. The slopes can look gentler than they are. That would make the planet appear larger and slower. A third limit sits in blending. Two nearby light sources can add together. The dip can then appear shallower because extra light fills it in. The boundary here is not a small mistake. It is a fundamental degeneracy. Different combinations of planet-sized chord position and stellar gradient can produce similar valleys. Without a strong handle on the star's brightness profile, the planet's silhouette can be misread. The mind can rest with this as a soft horizon. Indirect curves can be precise, yet they are still curves. They are not pictures. Another payoff follows from the horizon. Clean repetition helps separate effects. A true transit repeats with a stable period. Surface patterns shift with rotation and evolve. Over many cycles, the repeating valley can be isolated from the restless baseline. The shared curve strengthens. The shoulders sharpen into a consistent shape. The chord becomes better constrained. The planet's radius ratio becomes steadier. A final, slow scene gathers the geometry into one calm motion. A bright disk with a layered glow receives a passing shadow. The shadow enters as a thin crescent. It deepens into a quiet trough. It exits as a thinning crescent and leaves the glow smooth again. The valley that remains in memory is not a dramatic event. It is a measured curve. The next movement can follow the clock that this curve creates and show how small timing shifts reveal additional worlds. A repeating transit can keep time and still drift by a little. Transit timing variation is a repeat dip arriving early or late. In a quiet star system, one shadow crossing returns on schedule and then slips by about 5 minutes like a sheltered bay, where two gentle tides shift the moment of calm water. On another pass, the slip goes the other way, like a second tide cycle nudging the first, so the still point arrives sooner. The importance is plain. Small timing shifts imply unseen masses that share the same space. The scene begins with a bright disk that stays softly graded from center to rim. A small dark circle crosses on a familiar chord. The dip appears as a smooth valley. The valley returns again and again, yet the valleys are not perfectly stacked. Each one sits slightly left or right along the line of time, as if the same shoreline receives waves at slightly different moments. The first unlock is that timing can carry information even when depth stays unchanged. A planet can keep the same size and the same path across the star. Its silhouette can stay constant. The schedule can still bend. That bend points outward to other bodies in the system. Light behaves as if time is another axis of shape. A dip is not only how deep, it is also when it begins. When the start time shifts, something has changed in the orbit's pace or its position. The physical detail behind that shift is gravity acting as a tug that never turns off. When two planets orbit the same star, each orbit is not a perfect circle in isolation. Each orbit is a curve that feels small pulls from the other. The pull is strongest when the planets pass near each other in their paths. Even if they never come close in space, their relative positions change the force. The orbit can speed up slightly for a while. It can slow slightly later. The transits then arrive early and late in a repeating pattern. Another visual anchor settles in. Two faint rings surround a star. One ring produces the visible transit. The other ring carries a companion that never crosses the star from this angle. The unseen companion still tugs the shared balance point. The tug is quiet. The effect appears as a drift in the timing of the visible shadow. The second unlock is that the pattern of early and late can reveal the companion's period. If the timing shifts swing back and forth with a steady rhythm, that rhythm often matches how often the planets line up with each other. The lineup does not need to be exact, it only needs to repeat. When it repeats, the tug repeats. When the tug repeats, the schedule bends in a recognizable way. In that region, a signal would show a series of small departures from a perfect clock. Those departures can be plotted in mind as a slow wave around zero. The wave can be smooth. It can also have sharper bends. The sharp bends happen when alignments become closer. A calm analogy returns without tools or voices. Two tides enter a narrow inlet from different directions. The water level rises and falls with a combined rhythm. Sometimes the highest point arrives early, sometimes it arrives late. The shoreline is the same, the timing is not. This is how multiple gravity influences can shift an orbit's phase. The third unlock comes from resonance, and it remains gentle. Resonance is repeated timing that locks or nearly locks two orbits. Two sentences keep it grounded. One orbit completes about 2 loops, while another completes about 3. Their alignments recur often, and the tug pattern strengthens. It matters because repeated tugs add up. A single tug can be small. Many tugs in the same phase can grow into a measurable drift. The physical picture is of periodic nudges that arrive at the same orbital longitude. The orbit then oscillates around an average path. The transit times oscillate with it. A scale shift follows in a slow arc. The timing change is minutes. The orbital paths span millions of kilometers. The gravity field reaches through that distance without any physical contact. Over months and years, the small phase shifts can trace out a map of mass and spacing. The map emerges from a few minutes of difference against a backdrop of many hours of stable motion. Another visual anchor appears as a calm checkpoint. The star's brightness record shows a row of valleys. Each valley has nearly the same depth. Each one has similar slopes, yet their centers slide. The slide is not random. The slide follows a larger rhythm. Some valleys arrive earlier for several cycles, then they pass through on time. Then they arrive late for several cycles. The fourth unlock is that this timing method can weigh companions without needing their shadows. A non-transiting planet can remain invisible in depth. It can still announce itself by shifting the schedule of a transiting neighbour. Mass becomes a lever. A more massive companion produces larger timing swings. A lighter companion produces smaller ones. Distance matters too. Closer spacing makes stronger tugs. Wider spacing softens them. The timing signal therefore carries a combination of mass and architecture. It does not hand over a single number by itself. It still narrows possibilities. Another slow image holds the architecture. The transiting planet moves along its ring. The unseen companion moves on a neighbouring ring. At certain points, the two bodies fall on the same side of the star. Their combined pull draws the shared centre slightly. The transiting planet then reaches the crossing line a little sooner. Later, when they lie on opposite sides, the pull shifts the other way. The planet reaches the crossing line a little later. The schedule breathes. The shadow remains the same size. Now the limit of observation arrives and it stays specific. Timing shifts can be mimicked by changes in the transit shape. If the star's surface brightness patterns alter the shoulders of the dip, the inferred midpoint can shift. This is a limit in determining the exact center time of a transit. A slightly asymmetric dip can pull the best midpoint earlier or later, even if the orbit is stable. Another limit comes from gaps in the brightness record. If the beginning or end of a transit is missing, the center time becomes uncertain. The timing error can then resemble a small gravitational effect. A third limit comes from long-term drift in the baseline brightness. Slow variability can change the apparent depth and distort the fitted curve. This is not a failure of the idea. It is a boundary set by precision. The method depends on measuring minutes against many hours. If the curve is noisy, minutes can be lost. Another payoff follows from that boundary. Repetition helps again. Timing variations produced by gravity are coherent across many cycles. Random distortions are less coherent. When many transits are compared, the coherent pattern strengthens. The pattern can be matched to simple orbital relationships. The companion's period range narrows. The mass range narrows. The system's spacing begins to take shape. The tone stays calm because the mechanism is steady. Gravity does not surprise. It accumulates. The section ends with a soft turn toward motion in light. A transit shows a silhouette and a schedule. The next step can leave the shadow behind and listen to the star's subtle back and forth through shifting wavelengths. A star can seem perfectly still, yet its light can slide in a slow rhythm. Radial velocity finds planets by tracking the star's gentle back and forth motion along the line of sight. In that region, starlight does more than brighten darkness. It also carries a fine structure that stays mostly fixed unless the star is moving. When the star drifts closer, the light's wave spacing tightens. When it drifts farther, the spacing loosens. The first unlock is that motion can be read without any shadow crossing. A planet can remain unseen and still pull. The pull makes the star trace a tiny to and fro path around a shared balance point. The star does not travel far in space. The evidence appears as a repeating shift in the light's internal pattern. A slow visual anchor forms. The star's light spreads into a thin band of colours. Across that band lie many narrow dim seams like hairline cracks in glazed stone. The seams sit in stable positions when the star is at rest. Then the entire set slides together by a whisper. The slide reverses and returns again. The seams do not change their order. They simply drift as a group, as if the whole band is breathing sideways. Absorption lines are narrow dim bands where atoms remove specific colours. They appear because atoms favour certain energies. They resemble a lace of missing threads in an otherwise smooth fabric. They matter because the lace shifts when the star moves. The second unlock arrives in the direction of the shift. A shift toward shorter wavelengths indicates approach. A shift toward longer wavelengths indicates retreat. The pattern becomes a signpost for motion along one dimension. The number that sets scale can stay small and calm. A typical wobble can be about 1 meter per second, like a shadow edge creeping across a hillside at sunrise. The comparison keeps the pace gentle. The motion is slow in human terms and still significant in stellar terms. The star's mass is enormous, yet the planet's gravity still nudges it. At this distance, light behaves as a messenger that is sensitive to very small speeds. Another checkpoint image appears. A bright point sits in darkness with a faint surrounding haze. The haze is not a cloud. It is a way to picture the star's presence. Around that point, an invisible line marks the viewing direction. Along that line, the star shifts forward and back by an amount too small to picture directly. The forward shift corresponds to the colour seam sliding one way. The backward shift corresponds to the seam sliding the other way. The third unlock is that the shift repeats with an orbital period. A stable period suggests a stable orbit. The star's motion is not random. It returns like a slow pendulum that never swings wide. Yet the pendulum is not an object. It is the star's response to gravity. The orbit sets the rhythm. The rhythm sets the period. With the period, known distance becomes approachable again. Short periods imply tighter orbits. Long periods imply wider loops. A scale shift settles in. The seams shift over moments and hours. The orbit that drives them can span millions of kilometres. The system can persist for billions of years. The signal is a thin slide across a colour band. The cause is a massive dance of two bodies around a shared centre. Barycenter is the shared centre of mass in an orbit. It lies closer to the more massive body. It can sit inside the star or outside it. It matters because the star moves around it too. The fourth unlock is that mass enters naturally. A heavier planet pulls more strongly. The star's wobble speed grows. A lighter planet pulls less. The wobble becomes smaller. Yet a second limit appears alongside this unlock. The wobble speed measured is only the component along the viewing line. If the orbit is tilted, part of the motion points sideways and does not register in the shift. The measured mass can therefore be a lower bound. The true mass can be larger. The boundary is in projection, not in the physics. Another slow visual anchor holds that boundary. A circular orbit is imagined as a thin ring in space. From one viewpoint, the ring looks like a line. From another, it looks like an oval. From a nearly face-on view, it looks like a circle with little depth. The star's motion along the viewing line then shrinks. The seams slide less, even if the orbit is real. The fifth unlock comes from the shape of the signal across time. A simple planet on a nearly circular orbit tends to produce a smooth, sinusoidal drift in the seams. The drift is gentle and symmetric. A more stretched orbit can make the drift uneven. The star moves faster near one part of the orbit and slower near another. The seams then slide quickly for a while, then linger. This is a way to sense eccentricity without seeing an orbit. Eccentricity is how stretched an orbit is from a circle. It is like a loop pulled into an oval. It is like a bead moving on an elastic ring that is not perfectly round. It matters because speed changes around the loop. The physical detail behind this change is curvature and distance. When the planet is nearer, gravity is stronger, and the star's motion speeds up. When the planet is farther, the pull weakens and the motion slows. The colour seams respond with a drift that is not evenly paced. A calm scene appears. The band of colours stays thin and quiet. The dim seams glide steadily for a time, then they glide a little faster, then they settle again. No single seam misbehaves alone. The entire set moves as one. Now the limit of observation arrives, and it is specific. The seams are not infinitely sharp. The star's own atmosphere can broaden them. Rotation can smear them. Hot rising gas and cool sinking gas can distort their centres. These effects can mimic motion by changing line shapes rather than shifting the whole pattern. The limit is in distinguishing a true global slide from a local reshaping. A dark surface region can also alter the balance of light from different parts of the rotating disk. That can pull the seams slightly without any planet. Another limit is stability across long times. Slow changes in the star can drift the baseline. A very small planetary signal can hide within these changes. The boundary is set by how precisely the seam positions can be measured and how well intrinsic stellar variability can be separated. Another payoff follows quietly from that boundary. The most reliable signals repeat with the same period and phase over many cycles. Surface patterns tend to evolve. Their influence can shift in time. Over many orbits, the coherent planetary rhythm can stand out from the changing stellar texture. The measured wobble can then become a steady clue. It can combine later with a transit to lift the projection uncertainty. The section ends on a soft transition toward the star itself as a source of confusion. The next movement stays with the same light, but watches how surface features and rotating patterns can imitate a planet's pull. Starlight can imitate motion even when no planet is responsible. Stellar activity reshapes a star's light so the apparent radial motion can shift on its own. In that region, a star's surface is not a perfectly even glow. Darker patches and brighter patches form and fade. The surface also turns. As it turns, the patches ride across the visible face. The first unlock is that a moving patch can tilt the balance of light from one side of the rotating disk. One side of the disk approaches while the other recedes. When a dark patch covers part of the approaching side, the remaining light leans toward the receding side. The spectrum then shifts, as if the whole star is moving away. When the patch rotates to the other side, the shift can reverse. A slow visual anchor holds this gently. A luminous disk shows a soft gradient from centre to rim. Near the rim, a dark oval patch appears with a crisp boundary. The patch drifts inward as the disk turns. The overall brightness barely changes. The fine seams within the light change more. The second unlock is that activity changes line shape, not only line position. The dim seams in the spectrum can become slightly skewed. One wing of a seam can deepen while the other wing softens. This skew can pull the apparent centre of the seam. The result can resemble a true Doppler shift. The physical detail is a symmetry. A seam is not an infinitely thin cut. It has a width, and a profile. When the profile becomes lopsided, the center estimate slides. This is how a surface pattern can masquerade as orbital pull. An everyday analogy can stay simple and quiet. A polished marble has a darker vein. As the marble turns, the average sheen seems to drift. The surface is the same. The angle of the darker vein changes the balance of reflected light. The third unlock follows from rotation period. If a star turns in about 20 days, like the slow return of a familiar pattern, after 3 weeks activity signals often repeat on that timescale. A planet can also produce a repeated signal. The danger is that the two rhythms can overlap. When the rotation period and a planetary period sit near each other, the patterns can blend. The mind can accept this as a natural ambiguity. Two clocks can tick together for a while. Their combined beat can look like one. Another visual anchor arrives as a calm checkpoint. The star's disk turns. The dark patch moves from the left limb toward the center. The approaching limb contributes slightly more short wavelength light. The receding limb contributes slightly more long wavelength light. When the patch covers the approaching limb, that short side contribution weakens. The combined light leans long. When the patch crosses the center, the effect eases. When it reaches the receding limb, the effect reverses. The spectrum's seams breathe sideways in step with the patch. The fourth unlock is that brightness and velocity can be coupled. A spot can dim the star slightly. The same spot can also distort the spectrum. If a small brightness variation matches the velocity variation in phase activity, becomes a likely cause. Yet this coupling is not perfect. Bright regions can compensate for dark ones. The brightness can remain steady while the spectral seams still distort. This is why activity can be subtle and persistent. A star can look calm in total light and still hide complex surface contrast. Now a second activity source enters, and it stays gentle. Convection is hot gas rising and cool gas sinking. It creates a grainy pattern in brightness. The grains evolve. Their motion can bias the spectral seams. The physical detail is a field of tiny upflows and downflows. Upflowing gas tends to make light slightly blue-shifted. Downflowing gas tends to make it slightly red-shifted. The net balance can drift as the pattern changes. The fifth unlock is that a planet's signal repeats with strict regularity, while convection noise tends to wander. Convection can create jitter that is not phase-locked to a single period. Over short spans, it can mimic a low-amplitude planet. Over longer spans, it often fails to maintain the same rhythm. A visual anchor slows the scene. The star's face is imagined as a mosaic of softly glowing cells. Bright centers rise, darker lanes sink. The pattern shifts like slow boiling yet without any sharp motion. The spectrum responds with tiny changes in seam depth and width. The shifts do not line up cleanly from one cycle to the next. The sixth unlock is that time averaging can reveal coherence. When many cycles are considered, an orbital signal keeps the same phase and period. Activity signals often drift in phase as surface patterns evolve. This does not remove all confusion. It provides a way to separate stable clocks from restless textures. A scale shift arrives naturally here. The convection pattern can change over minutes and hours. The rotation can carry spots around over days and weeks. Magnetic cycles can change average activity over years. The star remains the same object. Its surface patterns span a wide ladder of timescales. That ladder sets a wide range of false signals. A soft limit of observation now becomes clear and specific. Radial velocity relies on measuring very small shifts in spectral seams. When seams are broadened by rotation and turbulence, the center becomes harder to locate. When seams are reshaped by spots and bright regions, a true shift can be hidden or exaggerated. The limit is not only noise, it is model dependence. A correction must assume a surface pattern and its evolution. If the assumed pattern is wrong, the correction can remove part of a planet's signal. It can also create a planet-like rhythm where none exists. Another limit sits in incomplete knowledge of the star's rotation. If the rotation period is uncertain, activity harmonics can be mistaken for orbital periods. These boundaries remain gentle. They describe why some detections require caution and patience. Another payoff follows from these limits. Activity leaves multiple fingerprints. It can change brightness. It can change seam shapes. It can change different seams by different amounts, because each seam forms at a different depth. A true Doppler shift moves all seams together. Activity often reshapes them unevenly. This difference becomes a quiet discriminator. A final visual anchor gathers the section into one calm image. A star turns with a dark oval patch near its limb. The patch rides across the graded disk. The spectrum's dim seams do not slide as a rigid set. Some seams skew, some broaden. The apparent motion signal rises and falls with the patch. The section closes with a soft transition toward what remains unknown. When activity and planets both influence the light mass, and tilt can become entangled. The next movement can show how geometry sets lower bounds and how multiple signals can tighten them. A wobble can be clear and still hide its true scale behind a simple tilt. The measured wobble from radial velocity gives a lower bound on a planet's mass, unless the orbit's inclination is known. In that region, motion is inferred from a shifting pattern inside starlight. The pattern repeats with a period. The amplitude of the shift suggests how strongly a planet pulls. Yet the pull is not measured in all directions. Only the toward and away component is carried in the wavelength slide. The first unlock is that an orbit can be real while its line of sight motion is small. A nearly face-on orbit keeps most of its motion sideways. The wobble then looks quiet. A massive planet can produce a small measured signal. A lighter planet on a more edge-on orbit can produce a similar signal. Projection is the quiet trick behind this. Projection is a three-dimensional motion seen in one dimension. It is like an ocean swell that looks tall from the side and nearly flat from head-on. It matters because the same true motion can cast different measured shadows. A slow visual anchor forms. A star and a planet circle a shared balance point in darkness. The star traces a tiny loop. The loop is round in space. From one viewpoint it appears as a narrow line. From another it appears as a small oval. The measured wavelength drift follows the line component of that loop. When the loop is seen edge on the line component is large. When the loop is seen face on the line component shrinks. The second unlock is that the lower bound arises from this shrink. The measured mass is the true mass scaled by the unseen tilt factor. The factor cannot be recovered from radial velocity alone. The signal carries the product of two things. It carries pull strength and viewing geometry. The result is an honest limitation rather than an error. A measured wobble amplitude can be about 3 meters per second, like a slow ripple that lifts a floating leaf and then lowers it again. The number stays small and calm. It shows why subtlety matters. The same amplitude could come from different true masses. It depends on the inclination. Inclination is the tilt of the orbit plane from the line of sight. When the tilt approaches 90 degrees, the orbit is edge-on, and the measured component is near the true motion. When the tilt approaches 0 degrees, the orbit is face-on, and the measured component becomes small. The third unlock is that transits solve this geometry when they occur. A transit implies an orbit that is close to edge-on. It does not require perfect edge-on. It requires a narrow range near that orientation. In that range, the correction from lower bound to true mass becomes modest. The world is then better constrained. Radius comes from the transit depth. Mass comes from the wobble amplitude. Together they imply density in a simple way. A dense world suggests a rocky composition. A low-density world suggests a larger fraction of light gases. The scene stays gentle. A bright disk is imagined with a small dark silhouette passing. At the same time, the internal seams of the light drift back and forth with the same period. Two independent rhythms lock to the same clock. This is the fourth unlock. When two methods share a period, the case becomes stronger. The mass estimate sharpens because inclination is no longer a guess. The radius estimate sharpens because the transit curve defines a size ratio. The combination can also reveal eccentricity effects more cleanly. If the wobble curve is uneven, the orbit may be stretched. If the transit timing remains steady, the stretch can be mapped to a consistent geometry. Another visual anchor arrives as a calm checkpoint. The star's spectral seams glide in a smooth wave. The wave reaches a peak and then returns. The transit dip appears at a specific phase of that wave. The alignment of dip and wave pins the orbit orientation. The fifth unlock is that phase ties the signal to a physical configuration. A transit occurs at a particular point where the planet crosses the star from this viewpoint. The radial motion at that same moment is constrained by the orbit. If the measured motion is not consistent with that constraint, the model must change. Perhaps the orbit is eccentric. Perhaps additional bodies perturb the motion. Perhaps stellar activity reshapes the seams. The phase relation becomes a test. It does not depend on any single number. It depends on coherence. This provides a quiet form of validation, yet a limit still remains, and it is specific. Most planets do not transit. Their inclinations remain unknown. For these systems, radial velocity cannot deliver an exact mass. The degeneracy is not removed by more precision alone. Even perfect measurement of the line of sight wobble leaves sideways motion unseen. Another limit is that stellar variability can mimic low amplitude motion. If the wobble is small, the uncertainty in separating activity from motion grows. In such cases, the lower bound can be uncertain as well. A third limit sits in long periods. A wide orbit can take years to complete. Over that time, the star's intrinsic changes can drift. The baseline of the spectral seams can shift. Distinguishing a slow planetary curve from a slow stellar drift becomes difficult. These limits are gentle horizons. They explain why some masses remain ranges rather than points. Another payoff follows from accepting the horizon. Statistical reasoning can still work. When many systems are considered, random orientations are expected. Most orbits are neither perfectly edge-on nor perfectly face-on. The lower bounds then cluster within a predictable factor of the true masses. Individual cases remain uncertain. Populations can still be inferred. The scale shift becomes wide and quiet. A few meters per second in measured motion can inform distributions across thousands of stars. Those distributions can shape an understanding of planetary architectures over billions of years. Another slow image holds this population view. Many stars sit as points. Around each invisible orbit, planes tilt at different angles like thin sheets in a dark current. Some sheets align and produce transits. Some do not. Some produce strong wobble signals. Some produce only faint ones. The same underlying physics plays out across each system. The observed sample is filtered by geometry. The final unlock returns to a practical calm. When a transit is present, the wobble becomes a mass measurement rather than a lower bound. When a transit is absent, the wobble still indicates that a companion exists and sets a minimum pull. Both are meaningful. Both are honest about what is seen and what is projected away. The transition forward stays soft. After motion and its hidden tilts, attention can shift to a different kind of alignment where gravity bends light itself and reveals planets through a brief, quiet magnification. In deep darkness, brightness can rise even when nothing grows brighter. Microlensing reveals a planet when gravity briefly bends background starlight into a stronger beam. At this distance, space contains countless straight paths of light. Most paths never notice a foreground mass. Once in a while, a foreground star passes near the line to a background star. The background light then curves slightly around the foreground mass. The first unlock is that the foreground star acts like a lens without any glass. The background star seems to brighten for a short time. The brightening fades when alignment ends. The event does not need a transit. It does not need the foreground star to move toward or away. It only needs a close pass in the sky plane. A slow visual anchor forms. Two distant points of light sit nearly on top of each other from this viewpoint. The nearer point is dim and steady. The farther point is dim and steady. Then the farther point swells into a soft glow, as if a thin ring is trying to appear around the nearer point. The ring never resolves into a sharp circle. It remains an imagined geometry. The brightness rises and falls as alignment slides past. Gravitational lensing is mass-bending the path of light in space. It is like a clear bubble in ice that redirects a sunbeam. It is like a smooth pebble underwater that concentrates a bright thread. It matters because a planet can add a second lensing imprint. The second unlock arrives in the shape of the brightening. A single foreground star produces a smooth, symmetric rise and fall in total light. The curve is a bell that peaks and returns. The width of that bell depends on how quickly the alignment changes. The peak depends on how close the pass becomes. A closer pass produces a higher peak. A wider miss produces a lower peak. The physical detail is curvature. Light rays are not absorbed. They are redirected. The redirected rays form a narrow region of enhanced brightness. That region sweeps across the background star's disk. As it sweeps, the total light grows and then relaxes. A scale shift settles in. The bending angle is tiny. The consequences are large because the source is far away. A slight curve in the path can send extra rays into the viewing line. A small geometry change can brighten a star that is many trillions of kilometers away. Another slow scene holds the timing. The alignment begins as a gentle lift. The light climbs with patience. It reaches a quiet maximum. It then descends with the same calm slope. The full event can last about 30 days, like a slow tide that rises and falls across a month. The number is not a decoration. It is a clue to the relative motion in the sky plane. It also hints at the mass scale of the lensing star, though not uniquely. The third unlock is that a planet near the foreground star can add a small deviation. The deviation is not a second bell that stands alone. It is a wrinkle in the main curve. The wrinkle can be a brief extra brightening. It can also be a slight dip within the rise. The timing of the wrinkle depends on where the planet sits in its orbit during the alignment. The strength depends on the planet's mass and its projected position. A visual anchor keeps this concrete. The main brightening curve rises like a smooth hill in darkness. Near the crest, a small notch appears. The notch is narrow. It passes quickly and leaves the hill smooth again. The hill continues to its peak. It then returns toward baseline. The notch is the planet's footprint. It is subtle, but it is specific. The fourth unlock is that microlensing can detect planets far from their stars. Transits favour close orbits. Wobbles favour shorter periods and quiet stars. Microlensing can catch a planet that sits at a wide separation because the lensing geometry depends on projected position rather than repeated cycles. A planet can be discovered even if it never crosses the star, and even if the star's spectrum is hard to interpret. This is a different doorway into the population. It is also a different kind of patience. The event does not repeat in any practical time. It arrives once and then disappears. Another slow scene expands the geometry. The foreground star passes in front of the background field like a drifting grain. As it passes, the background light is redirected into two broad arcs. Those arcs are usually too close together to separate. They blend into one brightening. When the alignment is near perfect, the arcs approach a thin ring. The ring is a boundary of enhanced light. The planet perturbs that boundary. It creates a smaller zone where rays crowd together more strongly. The fifth unlock comes from this crowding. The planet does not need to block light. It changes where light goes. The planet's gravity shifts the ray paths by a small amount. That small amount can steer additional rays into the viewing line for a brief time. The brightening then becomes sharper. The curve gains a kink. The kink marks the presence of a companion mass. The mind can hold this with an everyday analogy that stays natural. Sunlight in shallow water forms moving bands on sand. The bands appear because the surface curves and focuses rays. A small extra ripple can create a brighter stripe for a moment. The sand does not change. The light pattern changes because the surface shape changes. Microlensing is like that, except the surface is gravity, and the sand is the background star's light. It matters because the light pattern carries mass information. Now the limit of intuition arrives softly and clearly. The brightening curve alone does not uniquely identify the lens system. Different combinations of lens mass relative speed and distance can produce similar event widths. This is a limit of inference from one curve. A second limit is finite source size. The background star is not a point, it has a disk. When the lensing pattern sweeps across that disk, sharp features can be smeared. A brief planet wrinkle can soften into a rounded bump. The planet signal can then look smaller than it is. A third limit is blending. Light from nearby unrelated stars can add to the total baseline. The event can then appear less dramatic. The true peak can be diluted. These limits are not failures. They are boundaries set by what the light curve can contain by itself. Another payoff follows from naming the boundary. The planet signal is strongest when the lensing pattern has a sharp gradient across the source. When the gradient is steep, a small shift changes brightness a lot. When the gradient is shallow, the same shift changes brightness little. This explains why some events are sensitive to small planets and others are not. Sensitivity is not uniform. It depends on the alignment trajectory and the source size. A final, slow image gathers the method into one calm impression. A background star brightens as a foreground star drifts near the line. The brightening rises like a smooth hill. Near the crest, a narrow ripple passes through, then the hill continues. The light returns to baseline and the sky appears unchanged again. The next movement can linger on those sharp gradients and show how a planet can carve a more sudden spike into the brightening. When the lensing pattern becomes edged and thin, a microlensing event can look smooth, yet a planet can carve a sharp edge into it. Caustics are narrow boundaries of strong magnification, where a planet can imprint a brief intense feature. In that region, light behaves as if it is being folded and refolded by gravity. The folding is not visible as shapes in the sky. It is visible as a sudden change in brightness with time. The first unlock is that a planet can create a magnification boundary that is much sharper than the main lens curve. The main curve rises and falls like a gentle hill. The caustic feature can arrive like a narrow ridge crossing that hill. A slow visual anchor forms and stays unique. A background star is imagined as a tiny glowing coin. Across that coin, a thin, bright contour sweeps like a luminous thread. When the thread touches the coin, the total light surges. When the thread leaves, the surge collapses. The contour is the caustic. It is not a physical object, it is a boundary in the lensing pattern. The physical detail is an edge and a gradient. On one side of the boundary, light rays crowd into the viewing line. On the other side, the crowding relaxes. The brightness can change quickly because the gradient is steep. Caustic is a curve where magnification becomes very large. It is like a bright line under rippled water. It is like the sharp edge of a sunbeam focused by a curved surface. It matters because crossing that line reveals small masses. The second unlock arrives in the timing of the spike. The caustic feature can last about one day, like a brief weather front passing across a quiet landscape after many calm days. The number stays round and calm. It provides a sense of how thin the boundary is compared to the event. A full microlensing brightening can span weeks. A caustic perturbation can occupy a day or less. The scale shift is immediate. A tiny region in the lensing pattern can dominate the light curve for a short moment. The lensing geometry that produces it spans distances that are vast. Yet the decisive moment can be brief. Another visual checkpoint appears. The main microlensing curve rises as alignment improves. The light climbs toward a broad crest. Within that climb, a sudden, steep rise appears. The rise reaches a sharp peak. It drops just as sharply. The broad crest continues afterward as if nothing happened. The third unlock is that the shape of the caustic crossing encodes the source size. If the background star were a point, the spike would be extremely sharp. The background star is a disk with a finite radius. As the caustic line sweeps across that disk, different parts of the disk are magnified at slightly different times, the spike becomes rounded at its top. The rounding is not a flaw. It is a measurement of source size relative to the caustic width. This provides a quiet way to learn about the source and the lens. Another calm analogy holds the rounding. A narrow beam of light passes across a frosted window. When the beam hits a small frosted patch, the glow spreads out rather than snapping on and off. The patch has a size, the beam has an edge. The observed brightening is the convolution of the two. The fourth unlock is that planets can produce multiple caustic features. A planetary lens can create a set of caustic curves, sometimes in closed shapes and sometimes in extended arcs. The background star's path can cross one and then another. The light curve can show a pair of spikes or a spike and a dip. The sequence depends on the trajectory. It also depends on the planet's mass ratio to the star and its projected separation. The physical detail remains the network of boundaries. These boundaries can have cusps, points where the curvature changes abruptly. Near a cusp, magnification gradients are especially steep. A crossing near a cusp can yield a more complex feature. The fifth unlock comes from location on the pattern. A crossing through a straight segment yields a simpler spike. A crossing near a cusp can create an asymmetric feature with a shoulder. The shoulder is a lingering high magnification as the source slides along the gradient. This is still the same principle. It is a boundary effect. The light curve becomes a map of how the source thread crosses the lensing contours. A slow visual anchor holds the cusp without using sharp symbols. The caustic boundary forms a pointed petal shape in imagination. The background star's disk drifts toward the petal tip. As it nears, the brightness rises rapidly. As it passes the tip, the brightness lingers and then falls. The tip behaves like a tight corner in a flow of rays. The ray density changes fastest there. The scale shift widens again. A tiny planet far smaller than the lens star can alter ray paths enough to create a dramatic spike in the combined light. The planet itself remains unseen. Its effect is an edge in a pattern of bent light. This edge is defined by gravity over astronomical distances, yet it is traced by changes in brightness over hours. The sixth unlock is that the caustic feature can constrain planet mass ratio more strongly than a smooth bump would. A smooth bump could be made by many gentle changes. A sharp edge usually requires a specific lens geometry. The timing of the entry and exit across the edge can constrain the gradient width. The gradient width relates to the lens configuration and mass ratio. This does not provide a single absolute mass without additional information. It narrows the landscape of possibilities. Now the limit of observation arrives and stays specific. Caustic features are brief. Missing part of the spike can remove the most informative portion. If the brightness record is sparse during the day of the feature, the exact entry time and exit time blur. The gradient then cannot be measured well. Another limit sits in degeneracy. Different lens configurations can produce similar acoustic shapes when projected. A planet at one separation with one mass ratio can mimic another combination if the source trajectory differs. This is a limit of inference from a one-time event. A third limit is blending again. Extra light in the baseline can dilute the spike and make it appear smaller. Dilution can push the inferred mass ratio downward. The boundary here is in how well the baseline is known, and how well the source size is constrained. Another payoff follows from this boundary. The caustic crossing itself can help determine source size through its rounded top. With source size better known, the lens geometry becomes less ambiguous. The spike then becomes more than a dramatic moment. It becomes a calibrator. It anchors the model for the entire event. The main curve and the caustic feature can be fit together coherently. The planet's signal becomes less optional and more required. A final slow scene settles the mind. A broad brightening rises over weeks like a gentle hill. A thin, luminous contour sweeps across the background star's disk. For a single day, the light surges into a narrow ridge and then relaxes. The sky returns to its previous calm. The next movement can step away from one-time alignments and look toward cases where a planet's own light is separated from glare and seen directly as a faint companion glow. Sometimes the hardest part is not finding a planet, but separating its faint light from glare. Direct imaging detects a planet by resolving it as a distinct point beside its star. In that region, the star is an overwhelming source. The planet is a dim companion. The task becomes one of contrast and separation. The first unlock is that separation depends on distance on the sky, not distance in space alone. A wide orbit can place a planet farther from the star's glare in angle. A close orbit keeps the planet buried in the bright halo. Light behaves as if the star's brightness leaks outward into a soft cloud. That cloud is not a physical atmosphere. It is a pattern of scattered and diffracted light. Inside that pattern, a planet's glow can be hidden. A slow visual anchor forms. A bright core sits at the center of a wide, pale haze. The haze has rings and ripples. The rings are faint and concentric. The ripples fade with radius but never vanish completely. Far from the core, a tiny bead of light waits. The bead is steady. It is embedded in the haze's outer fringes. The bead is the planet's own light. It can be reflected starlight. It can also be thermal glow from warmth retained after formation. The second unlock arrives in the idea of contrast. Contrast is the brightness ratio between star and planet. It is like a small firefly near a lantern. The lantern floods the air with light. The firefly is real and still hard to pick out. The key is not only brightness, it is also the structure of the lantern's halo. If the halo were perfectly smooth, subtraction would be easier. The halo is structured. It contains speckles, small bright and dark patches that change with wavelength and time. The physical detail is interference. Light waves passing through an imperfect optical path form a mottled pattern. The mottling can mimic a point source. It can also swallow a real point source. The third unlock is that an instrument can suppress the star's core light to reveal the outskirts. Coronagraph is a method to block the star's central light. It creates an artificial eclipse inside the system. It is like placing a small disk in front of a bright lamp. It is like shading the center of a window so faint reflections beyond become visible. It matters because the planet sits in the star's outskirts. With the core reduced, the planet's bead can stand out. The visual anchor deepens. A dark circular mask sits over the star's core. Around the mask, the halo remains. The halo's rings become clearer because the core no longer blinds the scene. The planet bead sits near a faint ring edge. The ring edge is a diffraction feature. It is a boundary where light intensity changes rapidly. The bead can be confused with a bright speckle on that boundary. The fourth unlock is that planets move while speckles often change differently. A real planet shares the star's motion across the sky. Over time, the planet shifts position relative to the star in a predictable arc. The speckle pattern can shift with wavelength and optical changes. It does not follow the same orbit-like path. This difference can be used. The sequence of images can be aligned on the star and compared. A persistent point that rotates around the star is more likely to be a planet. A point that stays fixed in the halo frame is more likely to be a speckle. A number can set the scale gently. A directly imaged planet might sit at a separation of about 1 billion kilometers from its star, like a distance comparable to the span from the Sun to Saturn. Such a wide separation gives a better angular gap from far away. It also places the planet in a colder region. The reflected light can be faint. The thermal glow can dominate if the planet is young and warm. The scale shift arrives with calm. A bead of light separated by a tiny angle on the sky corresponds to a gap of 1 billion kilometers in space. That space contains a whole orbit. That orbit can take decades to complete, yet the bead can still drift measurably over years. The fifth unlock is that direct imaging can reveal atmosphere through color without needing a transit. A planet's light can be split into broad bands. Some bands can be dimmer because gases absorb specific wavelengths. The planet can show a slope in brightness with wavelength. The slope can hint at clouds or haze. The physical detail is scattering. Small particles can scatter blue light more strongly. Larger particles can scatter more evenly. A hazy atmosphere can smooth features. A clearer atmosphere can show deeper absorption. The mind can hold a slow scene of a planet bead that changes slightly with colour. In one band it looks brighter. In another band it dims. The star's halo also changes with colour. The planet's signal must be separated from that changing background. Now the limit of observation arrives and stays specific. The main limit is contrast flaw. Even with core suppression, residual starlight remains as speckles. Speckles can mimic a planet and create false positives. They can also drown a real planet. Another limit is angular resolution. If the planet lies too close to the star in angle, it falls inside the inner working region where suppression is less effective. The planet becomes inaccessible, not because it is absent, but because it is too near the glare. A third limit is time. Wide orbit planets move slowly. Confirming orbital motion can take years. During that time, background stars can also appear near the halo and mimic companions. Distinguishing a bound companion from a distant background source requires patient motion tracking. The boundary here is not in physics, it is in separation and time baseline. Another payoff follows from these limits. Direct imaging favours certain kinds of planets. Young massive planets glow more strongly in the infrared. Wide orbit planets sit farther from glare in angle. This selection is not a bias to hide. It is a lens on the population. It reveals a family of distant giants and informs how systems form and evolve at large radii. A final visual anchor settles the scene. A masked star core sits inside a faint ringed halo. Beyond the brightest rings, a small bead holds steady. Over time, the bead traces a slow arc separate from the halo's speckles. The next movement can widen from detection to consequence, and show how different methods complement each other to build full portraits of unseen worlds. A distant world becomes clearer when two different traces of light keep the same rhythm. A shared period across methods turns a faint hint into a coherent orbit with mass and size. In that region, starlight carries more than brightness. It carries timing, colour shifts, and subtle shape changes. A transit appears as a smooth dimming with a rounded bottom and sloped sides. A radial wobble appears as a gentle drift in the light's internal pattern. When both repeat on the same cycle, the orbit is no longer a single fragile interpretation. The first unlock is simple coherence. One repeating clock can be coincidence. Two repeating clocks that agree in phase are far less likely to be unrelated. A slow visual anchor forms. A bright disk holds a small clean notch that returns. At the same time, the light's fine structure slides left and right in a slow breathing motion. The notch stays shallow and smooth. The slide stays symmetric and calm. Together they suggest one body crossing and one body pulling. The connection is not a story. It is geometry and gravity converging on the same period. A small payoff arrives in the way ambiguity collapses. The transit implies the orbit is close to edge-on. The wobble then becomes a true mass estimate rather than a lower bound. The wobble sets how strong the pull is. The transit sets how large the silhouette is. The pair begins to describe not only an orbit but a physical object. The description moves inward from orbit to interior without ever seeing a surface. Density emerges from mass and size. Density is mass compared to volume. It is like how heavy a stone feels for its size. It matters because it hints at rock ice or gas. A number can sit quietly at the centre of this inference. A measured density can be about 5 times the density of water, like a smooth stone that sinks without hesitation. This single comparison unlocks composition without claiming certainty. A dense world suggests a large fraction of heavier materials. A low-density world suggests a swollen envelope of light gases. The second unlock is that density is a bridge between light and matter. A shadow gives size, a wobble gives mass. Their combination reaches inside a planet that cannot be resolved as a disk. The physical detail can remain concrete. A rocky world can have a strong gravity gradient from surface to core. A gas-rich world can have layered clouds with changing opacity. In both cases, bulk density is a coarse but meaningful fingerprint. Another slow scene holds the idea of layers. A sphere is imagined with faint concentric bands. The outer band is thin and bright. The inner bands deepen in tone. The boundary between bands is not sharp. It is a gradual change like sediment settling in calm water. The third unlock is that additional light signatures can test the same world. During a transit, some starlight passes through the planet's upper atmosphere if one exists. Certain colours can be absorbed more than others. The transit depth can then vary slightly with colour. This variation is not a picture of clouds. It is a change in apparent silhouette with wavelength. The physical detail is scattering and absorption in thin layers. A hazy layer can scatter shorter wavelengths more strongly. A clearer layer can allow deeper absorption features to appear. The method remains indirect. It still adds a second dimension to the silhouette. The silhouette is no longer only a circle. It becomes a circle with a faint wavelength-dependent edge. Another payoff arrives here. When the radius increases slightly at some colours, an atmosphere becomes plausible. When the radius stays the same across many colours, a high-altitude haze or a compact atmosphere can be inferred. The inference remains cautious. It rests on consistency across repeated passes. A new visual anchor settles in. Around the star's bright disk, a thin, almost invisible ring of twilight forms during transit. The ring is not a solid line, it is a gradient. It thickens in some colours and thins in others. The ring suggests a gaseous limb without ever showing clouds. The scale shift stays gentle. A change in a planet edge by a tiny fraction can imply thousands of kilometres of atmosphere. The observation is in minutes of dimming. The implication is in layers that persist over millions of years. The fourth unlock is that different methods fill different gaps in the same portrait. A transit favours close orbits and specific alignments. A wobble can detect non-transiting companions and refine masses. Microlensing can glimpse planets at wider separations in one-time alignments. Direct imaging can separate a distant companion's light when angular separation allows. Each method samples a different region of parameter space. The result is not a single map, it is a mosaic. Yet the mosaic gains strength where tiles overlap. An overlap between transit and wobble yields density. An overlap between wobble and imaging yields a true orbit inclination through the sky-plane motion. An overlap between transit timing variations and wobble can reveal additional companions that never transit. The fifth unlock is validation through cross-constraints. A planet-like signal that fits one method but fails another can be reinterpreted. A repeating transit with no matching wobble can suggest a very low-mass object or a diluted signal. A wobble with no stable phase coherence can suggest stellar activity. The limits become informative rather than discouraging. A calm limit of observation now arrives and remains specific. Each method carries degeneracies. A transit can confuse a small planet with a larger planet around a larger star if the star is not well characterized. A wobble can hide true mass behind an unknown tilt if no transit exists. Microlensing can blend lens mass distance and relative motion into similar curve shapes. Direct imaging can confuse a faint companion with a speckle-like residue or a background source. These are not only noise limits, they are inference limits. They depend on models of the star and on geometry. A second limit is selection. Transits are more likely for close orbits. Wobbles are easier for massive planets and quiet stars. Imaging is easier for wide orbit and luminous companions. Microlensing samples dense background fields and one-time alignments. A population built from any one method is filtered by these biases. The boundary here is not in the sky. It is in what a method tends to notice. Another payoff follows from naming selection. When biases are understood, a more complete population can be inferred by combining surveys. Close-in small planets can dominate transit counts. Wide-orbit giants can appear more often in imaging results. Microlensing can reveal planets at intermediate separations that are harder for transits. The combined picture becomes richer than any single list. The scale shift widens again. A tiny notch in light over hours informs the structure of a planet. A set of such notches across many stars informs how common certain worlds are across a galaxy. The time span of a measurement can be a few nights. The time span of a population trend can reach billions of years of formation history. A final visual anchor gathers the section into one quiet image. Several faint patterns float in darkness around a star system. A shallow dip returns with steady cadence. A slow colour drift matches that cadence. A thin atmospheric ring subtly changes with wavelength. Each pattern is incomplete alone. Together they interlock like currents meeting at a stable whirlpool. The next movement can widen further and explore how these interlocking methods shape a calm census of worlds, from hot close orbits to cold distant paths. A planet can be common and still remain unseen. Each method reveals only a slice of orbits, so a census depends on what light fails to reveal. At this distance, a star system is a geometry of paths and tilts. One path crosses the star and casts a soft notch in brightness. Another path never crosses, yet still pulls the star into a small back and forth. Another path sits wide enough that a faint point can separate from the star's halo. Another path aligns once, so gravity briefly focuses background light. The first unlock is that absence in one method does not mean absence in space. A crossing can be missing because the orbit is tilted. A tug can be hidden because the pull is small. A focusing event can pass without returning. A separated point can be buried in the star's mottled haze. A slow visual anchor forms as many stars wrapped in translucent shells. One shell marks crossing orbits. One marks strong tugs. One marks wide separations beyond the brightest rings of glare. Only parts of the shells glow at any time and most remain dim. The second unlock arrives with alignment. Transits are rare because the allowed tilt range is narrow. For a close orbit, the chance can be about 1 in 100, like one pale pebble among 100 in a shallow bowl. Farther out the range narrows even more. The silhouette is still a clean circle. The star is still a bright disk with sharp limb. The geometry simply offers fewer crossings. A small payoff follows. Short-period transits fill lists not only because they exist. They also repeat often, and repetition lets a shape strengthen. A calm scene holds that repetition. A rounded dip returns with the same depth. Its sloped sides meet the baseline without sharp corners. Noise drifts through the light, yet the same notch reappears. The third unlock shifts to the tug. A wobble does not require a crossing. It requires a planet that changes the star's line of sight motion in a steady rhythm. The physical detail is smooth reversal. The shift approaches a maximum, then passes through zero, then reverses. This method favours heft and proximity, because those make a stronger cycle. A gentle scale shift settles in. A tiny change in wavelength position reflects a planet's gravity in one system. Across many stars, many tiny cycles become a distribution of masses and periods. A slow, visual anchor replaces numbers with rings. Nested orbital loops surround many stars in imagination. Some loops are tight and fast, some are wide and slow, and their cycles unfold over years. The fourth unlock is that time becomes a gate. A long orbit can be missed because a full cycle is not captured. A partial cycle can resemble a different period. This is a limit of observation that stays concrete. Finite time coverage limits which periods can be trusted. Intrinsic stellar variability can mimic slow trends and distort weak tugs. A small payoff follows. Confidence rises when the same phase repeats more than once. Confidence rises when the tug keeps its symmetry while other fluctuations wander. Microlensing changes the texture again. It does not build certainty through repetition. It offers one alignment, and then it is gone. The fifth unlock is that this method samples wide and intermediate separations in projection. A planet can leave a brief wrinkle in an otherwise smooth brightening. The physical detail is a steep magnification gradient near a caustic boundary. A narrow crest can appear and fade within a day. The limit is specific. Lens mass, lens distance, and relative motion can trade off and mimic similar curves. Blended background light can dilute the crest and soften its edges. A small payoff arrives when many events are considered together. Single alignments become a population sample across crowded fields. A slow visual anchor holds this. Broad swells of brightness rise and fall in darkness. Most swells stay smooth. Some carry a brief sharp ridge that passes and leaves calm behind. Direct imaging carries the widest spatial feeling. It is not a shadow method. It is a separation method that seeks a faint point outside the star's broad halo. The sixth unlock is that wide companions are favoured because angular separation helps. Warm companions can also glow more strongly at longer wavelengths. The physical detail is the halo itself. It contains rings, gradients, and speckles that fade with radius. A planet must sit on a darker patch of that texture to stand out. The limit of observation remains contrast flaw. Residual speckles can mimic points and hide points. Resolution sets an inner boundary where separation fails. Wide companions also move slowly, so confirmation demands long-time baselines. A small payoff follows. These detections fill the outskirts that transits rarely touch. They hint at how distant giants can reshape inner architectures through gravity alone. Now the methods gather into one coherent idea without labels. Each technique acts like a natural sorting current. It is like a river that separates grains by size along its bends. Fine grains travel far into quiet eddies. Coarse stones settle sooner in stronger flow. In the same way, short orbit transits appear often because conditions favour them. Strong tugs appear for heavy close planets because the cycle is clear. One-time focusing reveals planets in regions where crossings are unlikely and cycles are slow. Separation reveals wide companions when the halo thins with distance. A final visual anchor makes this calm and concrete. Many star systems are imagined as spheres with thin orbital rings. Each method illuminates only certain rings, leaving others faint. Where two methods illuminate the same ring, the ring gains depth. Mass joins radius. Radius joins an atmospheric edge that changes with wavelength. The last unlock is that a census becomes a corrected portrait rather than a list. From that portrait, large-scale patterns appear across a galaxy. Those patterns point toward formation histories and long-term evolution. The next movement can drift into time and show how orbits and atmospheres change with age from early warmth to later stability. A planetary system can look still, yet it is a long, slow-motion sculpture. The present arrangement of worlds is a snapshot shaped by migration and resonance over deep time. In that region, gravity is gentle but persistent. It nudges, tugs, and trades energy across orbits. A pattern seen today can be the quiet end of a restless beginning. The first unlock is that detection methods record the current geometry. They do not directly record the path taken to reach it. A transit reveals a silhouette at one tilt. A wobble reveals a pull along one line. Microlensing reveals a chance alignment. Direct imaging reveals a separated point in a wide halo. Each is a clue to now. The story of then must be inferred from structure. A slow visual anchor forms. A young star sits inside a thin glowing disk. The disk is not uniform. It shows faint spiral bands and darker lanes. The lanes are gaps where material is thinner. They curve like soft brushstrokes around the star. Inside one lane, a small knot of dust brightens slightly. Farther out another lane is wider and calmer. The disk holds a gradient from bright inner regions to dim outer edges. The physical detail is layering. Dust and gas settle into a flattened plane. Within that plane, gravity can exchange angular momentum. The second unlock arrives with migration. Migration is orbit drift caused by disk gravity. It is like dunes sliding across a plane under steady wind. The dune is not pushed by a hand. It is reshaped grain by grain until the crest moves. In the same way, a planet in a disk can feel torques from slightly denser regions. The torque does not break the orbit. It shifts the orbit slowly inward or outward. It matters because a planet's final distance can differ from its birthplace. A small payoff follows. Wide separations found by direct imaging can point to worlds that formed far out or moved outward early. Close intransiting worlds can point to inward drift or in-place assembly. The inference remains cautious. Multiple paths can lead to similar outcomes. Another slow scene holds the drift. A planet clears a partial gap in the disk. The gap edge is sharp on one side and fuzzy on the other. A thin wake trails behind the planet, a spiral density ripple. Over time, the ripple winds tighter. The gap edges shift slightly closer to the star. The motion is subtle, yet the geometry changes. The third unlock is the disk's lifetime. The disk can persist for about 10 million years like a coral reef building a thick limestone layer in slow, steady growth. 10 million years is short compared to a star's full life. It is long compared to an orbit close to the star. During that span, a close orbit can repeat countless times. The disk then acts as a long-lasting sculptor. When the disk thins and disperses, migration weakens. The architecture can freeze into place. A gentle scale shift settles in. A small torque acting over millions of years can move a planet by vast distances. The planet itself travels fast around the star. The drift is slow compared to each lap. The drift is large compared to the size of the system. Another payoff follows from this. A planet found in a tight orbit does not require that tight orbit at birth. A planet found in a wide orbit does not require that wide orbit at birth. Present location becomes a clue rather than a verdict. The fourth unlock comes from resonance. Resonance is repeated orbital timing that locks into a ratio. It is like two ocean swells meeting so their crests return together. When periods align in simple ratios, gravitational nudges repeat at the same phase. The nudges can accumulate. They can stabilize spacing. They can also excite eccentricity if conditions allow. This matters because resonant chains can be built during migration. As planets drift, they can capture each other into regular timing. A slow visual anchor shifts from the disk to the orbits themselves. Several planets circle in a flat plane. Each orbit is a thin ring. The rings are not evenly spaced. Some are clustered like closely set ripples. At certain points the rings nearly touch in projection, yet they remain separated. A faint pattern of conjunction points repeats. The conjunction points form a rotating rosette. The physical detail is repetition. A particular alignment returns at predictable intervals. Each return delivers a similar gravitational tap. Another small payoff arrives. When transit timing varies in a repeating way, resonance becomes plausible. When wobble signals show multiple periods with near ratios, resonance becomes plausible. These are indirect traces of the same clockwork. The fifth unlock is stability as a boundary. Stability is long-term survival, without crossing orbits. It is like stacked layers of sediment that can remain undisturbed if slopes stay gentle. If slopes become too steep, layers slump and mix. In orbital terms, if eccentricities grow too large, paths can cross. Interactions can then scatter planets. Scattering can move planets outward. It can also eject planets into interstellar space. The limits of observation appear here with clarity. A present stable system does not prove a calm past. Past scattering can leave survivors that later settle. A present resonant pattern does not prove permanence. Resonances can break as disks fade or as tides act. A second limit is incompleteness. Small planets at wide separations can remain undetected by transits and wobbles. Faint companions can be hidden in imaging speckles. Microlensing can miss planets if the source size smears short features. The full architecture can remain partially unseen. A third limit is model degeneracy. Similar present configurations can arise from different histories. Migration and scattering can both place planets at similar distances. Resonance can be primordial or temporary. The boundary here is inference from a single snapshot. Another payoff follows despite the boundary. Certain structures narrow the possibilities. A tightly packed chain with near ratio suggests gentle migration and damping. A widely spaced pair with high eccentricity suggests stronger past interactions. A system with both close and small planets and a distant giant suggests multiple formation zones. The mosaic from different detection methods becomes more than a census. It becomes a set of constraints on how gravity shapes matter in disks. A final scale shift opens outward. A single system's arrangement encodes a few million years of disk sculpting, and perhaps billions of years of quiet evolution. Across many stars, these arrangements become a galactic pattern. The pattern hints at how often disks build chains. It hints at how often giants form far out. It hints at how often scattering empties inner regions. A last slow image settles into calm. The disk fades until only thin orbital rings remain. The rings glide in steady silence. The earlier spirals are gone. The system looks still again, yet its spacing carries memory. The next movement can soften further and gather the methods into a quiet resolution, leaving the mind with a stable sense of how faint light becomes knowledge. The most distant worlds arrive as patterns, not as pictures. A planet becomes real when separate patterns settle into the same quiet order. At this distance, light behaves as both a wave and a clock. It carries brightness that can dip. It carries a subtle drift that can reverse. It carries a rare focusing that can flare once and fade. It can also appear as a faint point beside a brighter glow. The first unlock is that each method reads a different face of the same geometry. A transit reads a silhouette. A wobble reads a pull. Microlensing reads a bend in space that briefly concentrates light. Direct imaging reads separation against a halo. None of these alone is a full portrait. Together they outline an orbit and hint at a body. A slow, visual anchor forms and holds steady. A bright stellar disk sits in darkness. A tiny rounded notch appears at its edge and glides across. The notch has a smooth floor and soft slopes. The disk returns to full brightness with no sharp jump. The same notch returns again after the same interval. A small payoff arrives with repetition. A repeating notch sets an orbit period without needing a visible planet. It also sets the orbit's tilt because the crossing is seen. When a second pattern matches that period, the picture tightens. A gentle drift appears in the light's internal structure. The drift moves one way, slows, then moves back. The reversal is calm and symmetric. The matching rhythm unlocks mass from pull and size from shadow. A planet becomes a density rather than a rumour. Density is mass compared to volume. It is like how tightly packed a stone is compared to a lump of ice. It matters because bulk makeup begins to separate into families. Another slow scene arrives around the planet's limb. The edge of the silhouette is not always the same at every colour. In some wavelengths the edge seems slightly larger. In others it seems slightly smaller. The change is small, yet it is consistent across multiple crossings. The physical detail is a thin atmospheric layer with a soft opacity gradient. Scattering makes the limb look thicker at some colours. Absorption makes it look thicker at others. A small payoff settles in. An atmosphere can be suggested without ever seeing clouds. A haze can be suspected when features flatten into a smooth rim. A clearer layer can be suspected when the rim changes in more structured ways. The inference stays gentle and bounded. It leans on consistency rather than spectacle. Now the scale shift widens without hurry. A change in starlight over hours can imply a layer that extends thousands of kilometres. The same layer can persist over millions of years if the planet holds it. A single transit is short. The structure it hints at can be ancient. Another visual anchor takes the mind farther out. A microlensing alignment unfolds like a slow breath. A background star brightens smoothly. Then a sharp ridge appears and slides past. The ridge has a steep side and a gentle side. It fades and the brightening returns to smooth. The ridge does not repeat. The event never comes back. The small payoff is that a single ridge can still point to a planet at wider separation. It can reveal a region of architecture that transits rarely touch. It can sample planets that orbit far from their stars. Inference here rests on shape and timing within one passage. The limit of observation is specific and quiet. Lens mass and distance can trade places in a model. Blended background light can soften ridges and hide smaller companions. The same curve can sometimes fit more than one physical arrangement. Another limit arrives with direct imaging. A faint point can sit near the edge of a star's glow. The glow is not uniform. It has rings, gradients, and speckled texture. A planet must be brighter than the local residue to stand apart. The physical detail is contrast against a halo that falls with radius. The small payoff is that wide companions can appear as their own steady points. Their separation can confirm that some giants live far out. Their slow motion can hint at long orbital times. Yet confirmation is slow because wide orbits shift gently from year to year. The next unlock ties the whole arc into a quiet principle. The cosmos is measured by indirect traces because distance erases detail. The traces behave like growth rings in a tree trunk. Each ring is thin and incomplete. One ring alone can mislead. Several rings together reveal a history of conditions. A transit adds one ring. A wobble adds another ring. A lensing event adds a brief ring from a single season. An image adds a ring from separation. When rings agree, the structure beneath becomes more likely. When rings disagree, the boundary of knowledge becomes clearer. A calm limit of intuition settles in here. It is tempting to imagine a planet as a visible globe. That image fails at interstellar distances. The mind must accept that planets become numbers and curves. The curves are shaped by geometry and noise. The numbers are shaped by models of stars and by incomplete sampling. A specific limit remains. Stellar flicker can imitate shallow dips and gentle drifts. Finite observing time can miss long periods. Alignment requirements can hide most orbits from transits. Contrast requirements can hide close companions from imaging. These are not errors in effort. They are boundaries set by physics and chance. A small payoff follows. Boundaries can be corrected in populations. Bias can be estimated and accounted for. Many faint signals can build a distribution that is more stable than any one signal. Patterns emerge across systems. Close-in small worlds become common. Wide-orbit giants become rarer yet influential. Intermediate regions become visible through microlensing where other methods thin out. Another scale shift opens and then softens. A single planet is inferred from a dip that may be about 1 part in 10,000, like one dark grain within a pale field of sand. A galaxy contains billions of stars, and each star can carry its own architecture. Yet the same basic rules of light and gravity apply across that vastness. The final visual anchor arrives as a calm composite. A star's disk holds a repeating notch. The light's inner structure drifts in step with that notch. A brief lensing ridge passes through another region of sky. A faint point sits outside a wide halo and slowly shifts along an arc. These scenes do not compete. They fit together like layers of clear water settling after a gentle swirl. The last unlock is quiet resolution. Exoplanets are found by letting light speak in several languages. Shadow drift, focus, and separation each contribute a phrase. When the phrases align, the presence of a world becomes stable enough to rest upon. The tone can soften now. The patterns continue in the dark without urgency. The mind can let the curves smooth out and fade into quiet distance.